What's up, guys? It's me, Sir Ernest, and today we will talk about what happens if we add two solutions to the wave equation with almost equal frequencies. So let's recall that if we have two solutions, y1 and y2, these two functions, y1 and y2, are solutions to the wave equation. This means that we can come up with a new result or new solution to the wave equation that is defined as the superposition of the two wave functions, because the superposition principle allows us to add two linearly differentiable equations and we still come up with the solution to the wave equation. Now, for example, we have two solutions, y1, which is a function of x and y, and this is equal to a e to the I kx minus omega t, while the second solution, y2, which is also a function of x and t, has the same amplitude as y1 and follows the same solution form. That's e to the I capital Kx minus capital omega t. So in this case, the frequencies omega and consequently your wave number k vary by small amounts, wherein capital K for y2 just differ by k, just differ with from k by delta k, which is very small, and capital omega is omega plus delta omega. Here delta k and delta omega are the difference between the wave numbers and the angular frequencies of the two waves by a very small amount. Okay, now, so forming this solution, we now have y will be equal to this plus this, and then factoring out the common amplitude, we now have a times e to the I kx minus omega t plus e to the I k plus delta kx minus omega plus delta omega t, like this. Okay, so splitting the exponential, we now have a times e to the I kx e to the negative I omega t plus e to the I k x e to the I delta kx e to the negative I omega t, then e to the negative I delta omega t. Now I'm going to do a sleight of hand here, wherein I'm going to split up the delta k's and delta omega terms on this side, and then on this side I'm going to add, or I'm going to multiply 1. Okay, so let me show that to you. So this is a times e to the I kx, and then e to the negative I omega t. But I'm going to multiply 1. using 4 exponentials. So we're going to multiply this by e to the I delta k over 2x and e to the negative I delta k over 2x. So this is 1, right? And then we're going to do the same for a term that involves delta omega. So this is e to the I delta omega over 2t and e times to the negative I delta omega over 2t. Okay? So this term is the same as this term. Now, we can see that if we're going to split this term and this term by halves of it, now have e to the I kx and e to the I delta k over 2x and then e to the I delta k over 2x. So this should be x. And then e to the negative I omega t, e to the negative I delta omega over 2t, then e to the negative I delta omega over 2t. So you will notice here my basic idea, because what I want is to combine these things. So I want to combine, for example, e to the I kx here times e to the I delta k over 2x. And I want to factor it out because there is also a similar term here. E to the I kx and e to the negative e to the I delta k over 2x. We can also do the same for negative e to the negative I omega t, wherein I'm going to this one and this one is common with this one and this one, right? So let's do that. So this is now equal to a times e to the I, then k plus delta k over 2x, and then e to the negative I omega plus delta omega over 2t. See that? And then this is multiplied with the remaining terms. So this is e to the negative I over 2, then delta kx minus delta omega t plus e to the, okay, good. This is I over 2 delta kx minus delta omega t. So you notice as these are very similar. In fact, if we're going to recall, let's recall somewhere here that e to the negative I theta plus e to the I theta is actually equal to 2 cosine theta, right? From your Euler formula. So we're going to use this here. So therefore, your function y, which is a function of x and t, is now written as a e to the I k plus delta k over 2x and e to the negative I omega plus delta omega over 2t times 2 cosine delta kx minus delta omega over 2, sorry, this should be t all over 2, which is a complex number. Of course, what's more important to us in this class are the real solutions. So if we're going to take the real part of this function, we end up with this expression. So this is 2a cosine delta kx minus delta omega t over 2 times, so remember this is e to the I kx plus delta k over 2x minus omega plus delta omega over 2t. And the real part of that from the Euler formula would be cosine k plus delta k over 2x minus omega plus delta omega over 2t. Okay, so the resulting wave function will have this form. Okay, so you will notice here that if there are generally two terms that we want to look into here, the first term would be this term. This is a what we call an envelope term, which I'm going to okay, and then this part is what we call your oscillating term. Now both of these terms are actually moving, okay, because this one has a velocity, this envelope term has a wavelength which is 2 pi over k, in this case delta k. On the other hand, this term, let's call this lambda 1. This term will now have a wavelength of, let's call this omega 2, lambda 2 would be 2 pi over k plus delta k over 2, which tells us that lambda 1 is greater than lambda 2. Okay. On the other hand, the frequency will be different. Now, how do we graph this one? And we can graph this one by, you will notice that the envelope term has a bigger wavelength. Okay, so let me put it here and let me write it here. Okay, so for example, this is your envelope term. Okay, so this is your envelope term. So the wavelength of this envelope term would be greater than the frequency. Will be the greater than the wavelength of the oscillating term. So within this envelope term, there exists this oscillation, which is smaller. Like this. Would look something like this. Okay, so in short, this wave, the black wave, would be the resultant wave. The envelope term doesn't really exist physically. Okay, so in short, if we're going to redraw this, it would look something like this. Okay, so this graph shows that when two wave functions having frequencies very close to each other that are superimposed, the phenomenon that forms is called the beats, wherein the beats refers to a slowly varying amplitude. Okay, so for example, this particle, while this oscillates up and down, its amplitude given by your envelope term also varies, because remember that this moves as well, while the resultant wave also moves. We call the motion of the resulting wave to be what we call yes, you guessed it right, that is your phase velocity. Now what about the velocity of the envelope term? So here we found again that the slowly varying amplitude is given by 2a cosine kx minus delta kx minus delta omega t all over 2, which can be rewritten as 2a cosine delta k over 2x minus delta omega over 2t. Okay, now we call the velocity delta. We notice that the velocity of the slowly varying amplitude of the velocity of the envelope term, let's call that u, to be equal to delta x delta t, which is in this case that's delta omega over 2 divided by delta k over 2, or simply, so this is delta omega over 2 over delta k over 2, which is simply delta omega over delta k. We call this is commonly known as your group velocity. So you will notice that when you say group velocity, that's the velocity of the amplitude term. The amplitude term or the envelope term, because sometimes we call this our amplitude term, because this is the term that describes the amplitude of your wave. So this is a slowly varying amplitude, and the velocity is given by group velocity. Okay, so there will be times that it's possible that the group velocity might be greater than your phase velocity, even if your phase velocity pertains to the speed of propagation of light. Because remember that in physics, nothing can exceed the speed of light physically, but you can actually exceed the speed of light. But if you're going to look into or consider the group velocity, which is not physical at all. Okay, so that's it. That's the difference between your group velocity and your phase velocity. Now, usually U and V are distinct. Group velocity and phase velocity are different from each other. Okay, but they can be the same if the medium does not depend on the medium itself. The velocity of the wave doesn't depend on the medium itself. That is, the medium is non-dispersive. Now, for your task, I want you to plot the real part. Okay, this equation, the real part of the wave function for any reasonable values of a, for any reasonable value of a, k, omega, delta omega, and delta k at time equal to 0. That's your first task. You can use any means that you want. You can use MATLAB or you can use Excel if you want. That's fine with me, as long as you will be able to plot this by reasonable values of your amplitude, wave number, angular frequency, as well as the difference delta k and delta omega at time equal to 0, and next would be at time greater than 0. So that means you may animate your real function or real part of the wave function at a later time t. Okay, so that's it. So that is our discussion on group velocity. Okay, so I hope you learned something today and you will be able to differentiate group velocity and your phase velocity. Okay, so I'll see you guys in the next video, because in the next video we're going to look into what happens now if I add more than 2 wave functions. Okay, so next video we'll talk about that. In the meantime, thank you for watching, and I'll see you guys in the next video. Bye bye.